Okay, so the talk I'm going to give today is about monitoring distributed data stream, and it's joined with Daniel Keren, who is a colleague of mine from Haifa University, and two of my PhD students, Yitzhak Sharfman and Guy Sagi. And this talk is based on several papers, but I wanted to mention that in my group, on recent years, we focus on large-scale distributed data processing and data mining, with emphasis on minimization of communication while doing that. And I also wanted to mention that there are other areas in which I work, because I originated in the systems and parallel and distributed computing domains. So I do grids, peer-to-peer network, distributed shared memory, storage, and so on and so forth. So my origins are more in the systems area. And I actually built some systems, in production systems, production grids, some nice stuff. All right, so back into this talk. In order to motivate this talk, let's look at an example. I'm going to motivate the talk through several examples here. Okay, so consider a mirrored website. And what you want to do, you want to follow the accesses on the different pages. So suppose you have a green page, a blue page, and a red page, and you want to monitor the frequency of accesses to the pages, so that when the frequency of accesses to the, let's focus on the green page, the frequency of accesses on the green page crosses a certain threshold, you get an alert. What is this alert used for? Maybe to put another copy of this page on another mirror, maybe to eliminate this page from one of the mirrors when it goes below the threshold. But the basic thing is that you want to monitor the average number of accesses, the frequency, the global frequency of accesses, where the accesses are distributed. Okay, so this is the simplest, perhaps, example of the problem that we are trying to attack. So here's first, there are a lot of accesses to the green page. It crosses the threshold from above. Then there are accesses to the blue and red, so it's below. And then there are again accesses to the green, so it crosses again the threshold from below. And what we want to have is alerts precisely when it crosses the threshold. Let us say what we are, in general, what we are going to solve, and then go back to the examples. So borrowing two slides. System model, we consider a set of data sources which we call streams. They are distributed either geographically or in the same room, but on different nodes. And they produce new data items periodically, occasionally. Sometimes they do not produce just a data item, but a collection of data items, so we call it a data vector. So a data vector is collected from each of these streams periodically. And the stream is infinite. Or we also consider very large data sets sometimes because we treat them the same as if they were streams. So usually you treat a stream with sliding or jumping windows. It will not matter for our results and our methods. And I will not get into this specific issue. So what is the problem that we are trying to solve? We are given a function over the average of the data vector. So collect all the data vectors from all the sources, take the average, compute a function on the average. We want to know whether this function crosses a specific threshold that is given. So this is actually a contiguous query. It lives all the time in the system. And it wants to know when the threshold is crossed. And our goal in life is to minimize the communication in the system while doing this. All right, so back to the interesting example. So in my home city, there's a lot of air pollution. And so what does the mayor do? It distributes sensors all over the city, and the sensors monitor the concentration of different air pollutants, carbon dioxide, sulfur dioxide, ozone, and so on. And there's a function called the air quality index function over the concentration of these pollutants, which is not a simple function, it's not a simple aggregation, which determines what is air quality. And when the air quality crosses a given threshold, it is out of the law. The law prohibits this function to cross a certain threshold, to be above a certain threshold. And so what does the mayor do when the air quality index, the average air quality index over all the sensors that are distributed in the city crosses this threshold from below? It gives a call to the refineries and tells them, please switch to a low pollutant fuel. So they switch to low pollutant fuel, the air quality index goes down, it goes back under the threshold, there's an alert going to the mayor, again calls the refineries and tells them switch back to a high pollutant fuel. Now, why don't they always use low pollutant fuel is something that I have a lot to say about, but it's a different talk, so bear with me. But anyway, this is yet another situation in which we want to monitor a distributed set of streams of information that are coming in.
What's the volume of traffic?
In this scenario, it's not big because there are only like 10 of those, or between 7 and 10 of these. And in this specific example, it's not really important, but I wanted to exemplify the problem here. In a moment, we'll see an example where the traffic is important, okay? And, okay, so there are some sensor networks examples, which we are going to skip today the sensors, if you don't mind. I mean, if you want to hear about them, just let me know. All right, so example number 4, which is a non-streaming example, a search engine database. So consider a distributed data center or warehouse with tens of thousands of nodes, horizontal partitions of the data. And in such an environment, usually the monitoring of what is happening produces a lot of data, orders of magnitude larger than the original data itself. The monitoring produces logs. The logs are enormous. And basically, what you want to do, you want to mine these logs in order to understand what do the customers want, what is the best way to optimize the system, what is the way to configure the system so it performs best. Okay, so the logs are enormous, we want to mine them. For instance, one of the questions that we want to ask when mining the log is compute the pair of keywords for which the correlation index is high. Okay, so this is going to help us in optimizing the solutions in the system and when working with the customers. So this is an interesting question, but of course, what Greg was asking is correct. What is the amount of communication that we produce? Because it might be that that the communication that you produce is not too high. So it turns out that we are going to think, in such a situation, you usually think about thousands of such processes that live together, and they consume a lot of bandwidth, and the bandwidth really becomes a scarce resource and really becomes a bottleneck. And so we really need to think about solutions that will optimize the operation, the computation of such a task. Okay, any questions about this example? Okay. Okay, so this is the last example that I want to make to turn into a running example. And this example considers a set of geographically distributed mail servers. Okay, and these mail servers, they want to collaborate with each other on identifying spam. So we assume that the mail server receives a stream of positive and negative examples. An example is an email. It is tagged as spam or tagged as not spam. The tagging itself is also an issue, but it's a different talk. Okay, so we assume that there is a stream of positive and negative examples. In the mail servers, there are many of them that are distributed across states or continents, and they want to collaborate on identifying spam. So how do they do that? They select a set of features, which can be words from the from the emails or concept in the emails. And they use these emails in order to build a spam classifier. How is a word selected? They need those sets to be as small as possible, but they need those words to be meaningful. What does it mean that the feature is meaningful? A feature is considered to be good if some function, which is called the information gain, is above a certain threshold. Okay, and the threshold is determined by the system manager. So, so here you can see, for instance, a stream of documents from 0 to 800. This is a Uninode situation. There is a stream of 800 documents, and there are and I consider in this graph you see three features: Bosnia, IPO, and February. Bosnia starts with a very high information gain, and then as the stream makes progress, Bosnia loses some of its capability to identify spam or not spam. IPO is always fairly good in identifying spam or not spam. And February starts very low, goes up, and goes down again. Later we will see why they behave in the way that they do. But the idea is that we set a threshold. The system manager sets a threshold, for instance, here, which determines that Bosnia and February, Bosnia is going to be here above the threshold, February is going to be here, and we want to know precisely when this feature crosses the threshold. Okay, so this is a running example. So what is this information gain thing? The information gain is defined on something that we call the contingency table, the statistics table. And the contingency table saves the following information. How much of the mail that came into the system was spam and included the feature? How much of the information that came in and was tagged as spam did not include the feature? How much of the information that came, the data, the email that came in was not spam, contains the feature, and so on. Okay, so this is a contingency table, and the information gain is defined like that. It does not really matter very much on what is the specific function. This is the way it is defined. Okay, so what do we want to do? We want to collect this contingency table from all of the different mail servers, and on their average, take the information gain on their average and decide whether it's above or below the threshold. Okay, so what is the problem? The problem is as follows. Consider two mail servers. One of them has this contingency table, which on all the mails that appeared and were spam, the feature appeared. And on all the mails that appeared and were not spam, the feature did not appear. So the feature is very good in identifying spam. So the information gain on this contingency table is the highest value of the information gain, which is 1. On the other hand, we have a mail server for which on all the mail that appeared and was tagged as not spam, the feature appears. And on all the mails that appeared and was tagged as spam, the feature did not appear. So again, in this server renders this feature very good for identifying spam when the information gain gets its highest value. But what happens when we take the average of these? The information gain is 0. It's the lowest value that the information gain can take. And this is the example that I wanted to put on the table for why the task that we take on ourselves here is very hard. Because there's no local indication on what is happening globally. And even worse, when you consider what is happening locally on general functions, the local indication can be misleading for what is happening globally. And we are interested in the global behavior. Okay, so the problem is clear. This is why I give this example in a lot of details, because I want you to understand what is the problem that we are having here. Locally, you have misleading indication about what is happening globally. All right, so what did people do with this problem? there's a large volume of previous work on aggregation functions, on linear functions, on sum and average. One of the early works was in Infocom by Danny Raz, who's sitting here, and there's a lot of follow-up works on this. Unfortunately, we found no previous solution for arbitrary functions, for functions that are not linear and not aggregates. Only naive algorithms. And of course, the naive algorithm moves all the data to a central location and process it there, which means that there's a lot of overhead in terms of bandwidth, power, cycles of the processors, the centralized resources that you need in order to process all this data, and also privacy issues, because none of you would like his email to be moved to a central location only because the server wants to collaborate with other servers on identifying spam. Okay, so maybe you think that non-linear functions are not important. Maybe they never appear. So, so apparently this is not the case. In industry, a lot of the time, in many occasions, you do need to process non-linear functions. You do need to process non-linear functions on top of a distributed environment. And I take this quote from Sigmod that I attended earlier this week from Sridhar Ramaswamy. He gave a keynote talk on extreme data mining, and apparently he also thinks that there's no, this quote says basically that there is no way that he knows about how to compute this non-linear function, which is fairly important for him. The link function is a function that he wants in order to compute the usefulness of putting a certain advertisement on a certain page. Okay, so the link function is very important, but it's non-linear, and apparently there's a hard problem in evaluating it while using the massive infrastructure that Google put up. All right, so this concludes the motivation and the example and the part, and now I'm going to delve into the solution, the geometric approach that we developed. I'm going to then look at some results, analysis, and optimizations. I'm going to skip sensor networks today, do some shape sensitivity stuff, which is interesting because it's geometric. I must tell you, you're going to see movies here. You're going to see geometric stuff, some drawings. For me, which I come from the parallel and distributed community, this was a very good, a very pleasant change. To be able to put nice drawings on a lecture. Anyway, and then perhaps we'll do some top K solutions. All right, so what is a geometric approach? So we looked at the problem and we said, because we are tackling general functions that can behave in any way, there is no, it is not good to look at the target domain. Let's look at the origin domain of the function. So we assume that the function is defined on a d-dimensional space, and on this space what we do, we color the whole space as follows. We color in white the places where the function gets a value which is below the threshold. We color by gray the places where the function gets a value above the threshold. So what we want to do when we have three local points of three different streams, and we have this average, what we want to do is this average ever crosses from white to gray, if it changes colors, we want to alert precisely when it changes the colors. Okay? And the problem is, of course, as you can see in this demonstration, that the local values can continue being white. As the stream makes progress, the local values continue being white, and they're very well in the white. But the global average gets closer and closer to the threshold until at a certain point in time it reaches the threshold, crosses it, and we want to get an alert precisely when it does. And again, the local indication in the different local streams are misleading because they think that the whole thing is white and they don't know what is going on. Okay, so our first observation is when you look at the origin domain of the function is that the average of the local readings of each of the streams is contained in the convex hull. Okay, so if you have 3 different readings, the average would always be in the convex hull. So we conclude that if we somehow know that the convex hull is monochromatic, then we also know that the color of the average is the same as the color of the different local points. Okay, so let's assume for 2 slides that we know how to compute that the color of the convex hull is monochromatic. Okay, that it's white. Then we get an idea, then we get a solution immediately. We know that the average is also white, and each of the local points knows the answer. The problem is that the convex hull will become very large. You see, the convex hull inflates more and more and more, and it's very, very large. We have a way how to control it, but the fact that the convex hull is inflated starts to be a problem, especially when the convex hull stops being monochromatic. You see, the convex hull stops being monochromatic, so our method of we do not know where the global average is, but we know that the convex hull stopped being monochromatic, so we issue an alert. But this alert is a false alarm. Okay, so it's a false alarm because there's a long time before the average will reach the threshold, and perhaps it will never reach the threshold. Okay, so we need to do something about the size of the convex hull. What can we do? The solution is that at times we can compute a global average. We spend some communication, we compute a global average, we let everybody know what the global average is, but since everybody knows the global point, the global information, the convex hull is now shrunk to 0. Why is this the case? Because consider these 3 empty diamonds. Okay, these were the values of the data of the different local streams at the time that the global average, the rectangle in the middle, the square the blue square in the middle, which is the global average, their global average was computed. Okay, now there was some communication going on. They computed the global average, and now the stream makes progress. The stream makes progress as there are drifts of the empty diamonds in different directions, from here to here, from here to there, and from this one to that one. And these drifts correspond directly to drifts correspond one-to-one for vectors which are drifts from the global average to these points, to these red points. Now, since everything is linear and everything is an aggregate, the average of the global values is actually also contained in the convex hull of the local drifts. So now, instead of monitoring this convex hull, this large convex hull, we only need to monitor this small convex hull. Okay, we only need to monitor it. If we know that it's monochromatic, then we know the result, and we know that no communication should be done. All right, so I told you everything, assuming that we know how to monitor the monochromaticity of convex hull. Wait, there's more to this film. So you see, once it becomes non-monochromatic, once the convex hull becomes non-monochromatic, we again compute again the global average, and again start with drift vectors which are small, and the convex hull shrinks again, and so on. And we can issue alerts precisely when we cross the threshold. Okay, so now I need to tell you how I monitor the monochromaticity of the convex hull. So, what we did was to prove a theorem. And the theorem says as follows. Suppose you have a set, suppose you have a polygon in R-dimensional space, in D-dimensional space. And now compute a certain, and now take a point. The point can be inside the polygon, outside the polygon, does not really matter. Okay? And now take the distance from each of the vertices of the polygon to this point and make a sphere whose diameter is this distance. Okay? So here's one sphere, here's another sphere, here's another sphere, and so on. And the theorem says that the convex hull is bounded by the union of these spheres. Okay, so this sounds like a very natural, very simple, and straightforward theorem. However, apparently it was not known to computational geometry people. We could not find it in any of the computational geometry books. When we talked with stars in that area, like Mikra Sharir, he said that he termed it a sensation, that it was not really known. When I talked to other people, they said that maybe Euclid already knew the two-dimensional version of it, but unfortunately we don't have him here to ask. So people came with several proofs to this theorem, yet we did not find it in anywhere, so we assume, so we get the credit for proving it. So in two-dimensional, it's really relatively easy to prove. It's like high school kind of thing, trigonometry. In higher dimensions, there were several ideas how to prove it. I'm not going to give you the proof, although we have a few very easy ones. But what's important here is that this theorem gives you a tool how to come up with local constraints. So each of the vertices here, if you consider it to be a source, a data source, each of the vertices here can by itself compute something which will tell it whether it needs to trigger some communication or not. If none of them trigger communications and there's no communication, what is this constraint? The constraint is whether this sphere is monochromatic or polychromatic. Okay? If this sphere becomes polychromatic, then it means that maybe some of the points inside the convex hull are switch colors, and it means that this guy should trigger communication. But if nobody triggers communication, it means that all the spheres are monochromatic and the convex hull is also monochromatic. Okay, so this was the idea, and the algorithm that follows is just pick an estimate vector, compute a global average, and now take the drift vectors, and each of the origins of the data sources will compute whether the current sphere is monochromatic or not, and as long as it's monochromatic, there's no communication that needs to be done. Okay, so the algorithm goes as follows. You can see that each of the data sources compute the monochromaticity of a sphere. If all of them are monochromatic, as long as all of them are monochromatic, the convex hull is monochromatic, and they do not need to do anything. At a certain point of time, they will become polychromatic, and which will trigger communication event, and they will again compute the global average, and again, and again, and again, and so on. I always like to look at those movies, I must say. It's hypnotizing. Anyway. Okay, so let's look at some results when applying this algorithm. We looked at the Reuters corpus with 800,000 news stories between August 96 and August 97. And unfortunately, at that time, there was no tagging for spam or not spam, but there was tagging for industrial and corporate industrial or non-corporate industrial. And we decided that this tagging simulates quite well spam or not spam. So, so we use this. So when I say spam or not spam, I mean corporate industrial or not corporate industrial, and vice versa, okay? All right, so we looked at 3 different features, and at that time, the war in Yugoslavia was just coming to an end, so you can see that at the beginning, the word Bosnia was a very good discriminator in those news documents for whether this is an industrial story or whether it's not industrial story. Okay, whenever Bosnia appeared, it was probably a not industrial story. All right, and if you look at IPO, it's always a relatively good indicator for industrial stories. And if you look at February, at the beginning, it is in August, half a year before February, it is a very bad identifier. Slowly, during the year, there's this peak here, which we do not know to explain. Slowly, during the year, it gains power. And finally, it becomes, in February, it becomes a very good discriminator for industrial stories. And then it drops down again. And I don't know how to explain this. I don't know. If you have an explanation, I would be happy to hear it. But anyway, this is why they behave in this way along the stream. And if you see, you look now at the amount of messages, the amount of communications that we need in order to plow our method, you can see that the naive algorithm requires about 9/10 of the total amount of documents because we have here 10 nodes, okay, collaborating. Okay, so the naive algorithm needs to move all the information from 9 of them to 1 of them, so it does 9/10 of the total communication. And if you look at what happened with our algorithm, you'll see that basically in thresholds that are barely met, the communication drops down to practically 0. Okay, so these are the extreme threshold in this to the left and to the right. Okay, but if you look at the middle, there's some places where we can save very little, like 3 or 4-fold in the amount of communication, which I call very little. So why is it the case? So if we look at February and we set a certain threshold, it usually crosses this threshold only once or twice or 4 times max. Okay, and if we look at Bosnia, there's some here it crosses thresholds very rarely, but here it starts crossing this threshold. It vibrates on the threshold of 0.0031 or 32 a lot of the time. So you can see that if you set the threshold to 0.003 something, Bosnia gets some high values here of communication, because every time we will cross the threshold, there's some communication going on several times, because the spheres will stop being monochromatic. Okay, and the same with IPO. IPO is very good on extreme threshold, but when you get to the threshold of 0.003 around here, then it vibrates and crosses the threshold all the time, and so it produces the algorithm produces a lot of communication. Okay, so how can we help here? Of course, one way to help is to to use the trade-off of accuracy vs performance, give away some accuracy and get more efficiency by setting an error margin around the threshold value. The error margin is determined by the dashed lines, the white dashed line and the gray dashed line. And now we are going to issue alerts only when we are going to say that the sphere becomes non-monochromatic only when it crosses the dashed line. Okay, so we get an alert when the global average crosses the dashed line, the dashed gray line. So that's a high watermark and low watermark. okay? And you can see that for the threshold 0.003, IPO gains much more than the others by activating this method, precisely because it vibrates all the time on 0.003, and when you set error margins, it gains a lot of profit, okay? And the other gain less. Okay. So it goes as follows. You can count the number of times the spheres becomes more and more chromatic, and you'll get 7. And when you set error margins, you'll count and you'll see that it's only 4 times, I think. This is just to show you once again this movie, okay? Another way to stabilize IPO on such threshold, and by the way, this is not a real problem because you always want to monitor function on extreme values. You don't want to monitor function on thresholds that are always crossed. It's irrational. Okay, but if you do, nevertheless, if you do, then something else you can do is you can aggregate messages, aggregate the data items that are arriving at the data source, and enlarge the window size, and you can see that when the window size grows, IPO gets more profit than the other feature, once again. Okay, because it stabilizes, and when it stabilizes, it crosses the threshold less number of times. With respect to scalability, it's of course different between the different thresholds. This is 0.003, which is very hard on Bosnia and IPO, so you can see. But basically what you see here is that the amount of communication that is required in our mechanism is also linear. It is best activated on thresholds that are not met a lot of times. If you look at the performance analysis, of course, the performance analysis is the first thing that performance analysis depends on is the function itself. So if the function look in this way, it is much worse than if it looks this way, of course. And there's nothing you can do. Okay, so this should be clear up front. However, the efficiency also depends on two or three other factors. The first of them is the distance between the global average and the surface, the zero surface of the function. Okay? If this is large, then the probability of violation is smaller. And when this is small, the probability of violation is larger. It also depends on how, what is the variance of the local data streams, how do they depart from the global average. When the variance is high, then the spheres are large, and there's a higher probability that the spheres will become non-monochromatic, and vice versa. Okay, so if you want, if you like mathematics, you can look at these bounds and see that indeed the probability of violation increases, the number of the amount which show itself in the amount of communication increases with the variance of the different sources, and is reduced by the distance with the increase of the distance of the global average from the zero surface, and is also decreased by something else, which is the size of the window that you take. One other nice features of this, nice things about this methodology is that you do not really need to go global communication. Okay, suppose you have some troublemaker here that has a large variance and is becoming polychromatic every now and then. All you need to do is to find somebody else who's behaving very well, and average these two, make sure that the one that behaves well averages the one that is not behaving well. Okay, and when they average their values together, you get this point. They both know about this point now. Now the convex hull is this convex hull, and the two other spheres remain the same. They did not hear about what was going on, but still you get something which is monochromatic, and no global communication needs to be taken. There's some issue with the computational complexity of calculating monochromaticity of spheres. It's a painful issue. And we have many different ideas how to solve it. There's some functions that you can compute a closed form solution, some numerical methods, some offline computation and caching that you can do. I don't want to get into this this minefield. Something else that you can do is to consider monitoring many features. Until now, I was talking about monitoring a single feature. What happens if you're going to monitor many features? If you're going to monitor 4,500 features already, you meet the performance of the naive algorithm, because the naive algorithm, it does not matter for the naive algorithm how many features you monitor. Okay, so you somehow want to be able to monitor together all the features, and not one by one. Okay, so what can you do? In this example, we look at chi square, but chi square is a different function that sometimes used to do the same as information gain. But it doesn't really matter. The important thing is that, okay, so let's look again at the contingency table. Okay, it contains certain values. And now what we can do, we can apply a certain transformation. And the transformation leaves x4 the same as it is, but instead of x1, x2, in x3 it defines three new values, y1, y2, and y3. Okay, each of them is the sum of two previous values. And can one of you see why this transformation is advantageous for following many different features instead of just one at a time? Okay, look at this one. Y1 is a sum of x1 and x3. So basically, y1 becomes the amount of spam in the system. So when you look at the data in this coordinate system, y1 determines how much spam is coming into the system. And spam turns out to come in bursts. So it might be that a certain feature has this coordinate, grow its sphere, and become non-monochromatic. But if this coordinate grows large, it means that it will grow large for all other features. So when we have a communication event, when you have a violation, we can look at this feature, see if this was the one that caused the sphere to be non-monochromatic, then we take care of all other features at the same time. It looks the following. I'm going to show you now how the stream, the Reuters stream behaves with the new coordinate system. You can see this is the manifold of some threshold. And some of the features go across the manifold. They need to be alerted, and they go in y2 and y3 directions. But in the y1 axis, which is the z-axis, what you have here is the amount of spam, and you can see that the amount of spam grows and it comes in bursts. All of a sudden, there's a large amount of spam in the stream, so everybody go up, and of course the sphere grows very large for all of them together, and then they go down, and again the sphere goes very large for all of them together. So you can, in this respect, a violation that comes from the fact that they move in the y1 axis, you can treat all of them together and reduce the amount of communication by a great deal. Okay, so we moved through the results, analysis, optimizations. We moved through the sensor networks, and we get shape sensitivity and okay. How much time do I have, by the way? I don't see any.
So 7 minutes till.
7 minutes. Okay, so there's all kind of geometric games that you can do. One thing that you can do is to feed the cover to the data. Okay, so you have the data coming in, the variance, we already talked about the variance, it goes in different direction, and this is a global average. So probably the direction where the different sources move is along this axis, along the PCA. Okay, so what you can do is to use a covariance matrix in order to align the data along the axis. You are going to inflate the data, again by using the covariance matrix, so that all axes have the same influence. And now you can compute a cover to what you got, what you received, and then you're going to apply the inverse transformation, squeezing back the inflated creature and turning it again to its original state. And now you can see that you have a new cover to the convex hull, which is much, much more compact than the original cover. Okay, the original cover had a lot of area, which results in a lot of false alarms. Okay, and this is a much more compact solution. Okay, so this is one thing that you can do. You can feed the cover to the data, and we can prove some optimality results concerning this, concerning the ellipsoids that are resulted. Something else that you can do, if you have two local values and you have the global average, sometimes the spheres, the resulting spheres, are non-monochromatic. Why choose the global average here? Maybe we can choose another global average. For instance, this one, the green one. The spheres become larger, but they are now monochromatic. Okay. What did we do here? We pushed the global average away from the surface. Okay, what does it mean to push the global average away from the surface? The safe zone is defined as a geometric place of all the points from which, if you draw a sphere with a diameter is the distance between this point and the blue point, you will get a sphere that is monochromatic. Okay, so the safe zone is all the geometric points, and you can see that when we move away from the threshold, the safe zone becomes larger. Okay, this is the safe zone of the blue point. This is the safe zone of the green point. And as you go into the middle, somehow we need to define a middle, the safe zones grow larger. How much larger can they grow? We need to push the point, the global reference away from the threshold until the distance from the threshold starts to be smaller, because it starts to come here. Okay, so we push it away until the point where the distance from the threshold starts to be smaller. So how, what is this? What are all these locations that are equidistant from the threshold, from all directions from the threshold? They are usually called the skeleton or medial axis. If you look at the threshold and you take all equidistant places and you paint them in the same, you paint them in the same color, you clearly see the medial axis here in the center, in the so-called center of this creature that this function defines. Now, if you apply these two optimization, fitting the cover to the data and fitting the cover to the function, the original performance that you had, this is the amount of communication that we had before with spheres, becomes much lower, and lowers all the way to the blue curve here by 2 or 3 orders of magnitude. And so the question remains, how far can we do? How better can we do? We can show a theoretical optimal lower bound on this method, which is a red line. The theoretical optimal lower bound relates to all the local methodologies that use convex hull. Okay, so if you use convex hull, you will always bump into this lower bound. And it goes as follows: whenever the convex hull crosses the threshold, you have communication event. Okay, so you count all communication events that are produced by the convex hull crossing the threshold, and you get this lower bound. So you see that we are fairly close. Not a lot of space left for further optimization. Regarding the top K, so there are some motivating examples here. There is an example of the, you have many stores that are distributed geographically, and at the end of these days there are all these purchases that were done in the stores, and each of the purchases is a transaction, contains a lot of items. And for instance, at the end of each day, the manager would like to know the top K sold product pairs, or the top K pairs of products that correlate to each other the most. Okay. Another example is if you have a this is a previous example that we had at the beginning of the talk, where you have where each node maintains local statistics of queries on a search engine from the previous day. And every day you want to know what are the words that imply each other the most in the queries that appeared in the previous day. Okay, in a distributed setup, you have the count of words, and you want to know the pairs of words that imply each other in queries that correlates to each other the highest in the queries. Okay, so we use the correlation coefficient equation function, which is defined here, and has many nice properties. In general, it takes a value. It has a value in the range of -1 to 1, and if the value is higher than 0, it indicates that the terms tend to appear with each other, together with each other, and if the output is 0, if the value is 0, it indicates that there's no correlation between the terms. And if the value is less than 0, it indicates that the terms tend to exclude each other. Okay, and so this is precisely what we want to know. And it also has a nice property which helps us later, that if we restrict it to the domain where if A and B appear, where the region where A and B appear together is less than or equal to any of the regions where A appear alone or where B appear alone. So if we restrict it to this region, it becomes monotonic. It monotonically decreases with the amount of appearance of A and the amount of appearance of B, and monotonically increases with the amount of appearances of both of A and B together. Okay, so there's some example here. If you have 2 nodes, 1,000 of queries on each, and on both of them, and both A and B appear 100 times on the first node, and both A and B appear 400 times on the second node, then they get the same value for the correlation function in each of these nodes. But when you look at the average, of these, you get a very different value, which maybe is above the threshold. So again, you can see here local indications that are misleading in this function. It's not linear, it's not aggregate, it's not frequent items. Okay, so we get a 4-phase approach. I don't want to get into the whole algorithm. The only thing that you need to know is that the algorithm, which is reflecting on similar algorithms for top K that we know in the literature, is done as follows. It compute a lower bound on the value of the top k, and then locally prunes out, filters out all those objects that don't even have a chance to cross this lower bound, that will never be able to cross this lower bound. Okay, so the first two phases compute lower bounds, and then the next phase, the third phase, goes through all the objects locally in each of the nodes and locally prunes out those objects that don't even have a chance to cross the global threshold. How do we do that? With a nonlinear and non-aggregate function. We can do it through the geometrical approach. And we also use some domination relation. I will not get into this. And the fourth phase is also not very important. So what do we do? Suppose these are the values, the local values of a certain object in each of the nodes. And what we want to know that the value of this object, when everything will be collected to a central location, the global average, when you operate on it with a function, will not cross the threshold. What is the threshold? It's the lower bound on the top k. Okay? So how can we do that? What we do is we get a global reference point. A global reference point is the origin in this case, and it works well. I don't have time to go into this, but it works well. It's the origin in this case. And now in each of the local data sources, we compute all the values, the maximal value of the correlation coefficient on this sphere. And here we compute the maximum value of the correlation coefficient on that sphere, and so on and so forth. So if in one of the nodes, the correlation coefficient on any of these points crosses the lower bound that we have on the top k, then it sends an alert about this object, and this object needs to be gathered together and considered to be a candidate, a viable candidate for the top k. Okay, but if not, then we also know that the global average was covered, and we do not need to do any communication, to produce any communication. Okay, so this is yet another usage of this geometrical interpretation, and of course we can go through all kind of optimizations. I don't have time to get into this. And the domination relation allow us also not to check all of the domination relation result from the fact that the function was monotonic in the region of interest. Okay, so they say that if you have a very high value for an object which is dominating another object, it dominates another object because all the coordinates are larger than this object. Okay, so in a monotone function, or a function that is monotone on the region of interest, this object is dominating that object, and we do not have to look even in this object. So the filtering, the local filtering itself, process itself, is also very highly efficient. And so we tested it on queries from a search engine, from AOL search engine, several billions of queries. You can see here sample correlations for certain pairs of words. And the communication drops down. It's not important to look at the graph itself. Basically, with large data, with few billions of queries, we converge to savings 3 orders of magnitude in the amount of communications that is needed. And we think that when the data is larger, the larger the data, the more saving we can do. And we can also save on I/O cost. With this amount of data, the local pruning in each of the nodes considers only a small fraction of the total number of keyword pairs. Okay, and only tenth, I think. And with the larger data, I think that we will be able to save even more. And basically, that is it. There's a lot of current and future work going on the foundations of all this, the testing, the complexity of the testing, monochromaticity, some ideas about how to extend this to peer-to-peer kind of networks, large-scale networks, how to do non-threshold computations. Top K on streams is a straightforward extension of this work. Some stream fusion problems and implementations and so on. And okay, so that's it. Any questions?
So this is a Dijon level?
I wish.
So I have a question. In one of your first slides, you talked about average as the information from which you will later compute the quality of the indicator. So I was wondering whether one could consider provide more information about the distribution of the inputs. Maybe compute higher moments, or so then you can perhaps get a more more accurate shape of the input, and then you can say how well it is, whether more accurately whether it is a good indicator.
I agree. I mean, this is a very good question, and although we were focused on solving the global average case, the distribution which gives which would you would like to know locally what is going on in many situations. And you would like to know that if a certain store of Kmart is doing completely different, is an outlier in the other stores, you would like to know. Of course, this results in a very different set of algorithms, very different approaches, which are interesting by themselves. And unfortunately, I don't know of a lot of work in this direction. Other questions? Okay, thank you. Thanks.